So friends, in the last lecture, we talked about the Otto cycle and we said that Otto cycle is an ideal cycle for petrol engine. For the diesel engine, we can think of another air standard cycle which is called as a diesel cycle, and the diesel cycle again has got four processes. Let me call them as 1 to 2, which is isentropic compression, 2 to 3 is the heat addition process, but mind well, this heat addition now is at a constant pressure. You know that in the Otto cycle, the heat addition is at constant volume. In the diesel cycle, the heat addition is at constant pressure. So this is how, and this is where the diesel cycle differs from the Otto cycle. So this process is different than what is in the Otto cycle. Okay. 3 to 4 is similar to that of the Otto cycle, that is, it would be an isentropic expansion. And finally, 4 to 1 would be similar to the Otto cycle, that is, it is equal to the constant volume heat rejection. So these four processes, that is isentropic compression, constant pressure heat addition, isentropic expansion and constant volume heat rejection, they together constitute what is known as a diesel cycle. So let us now represent them on the pressure volume diagram and the temperature entropy diagram. So let me draw this, represent this on the pressure volume and the temperature entropy diagram. Okay. So this is pressure, vertical is pressure, horizontal is volume, vertical is temperature, horizontal is entropy. So let us represent first the process 1 to 2. Now 1 to 2, as earlier, as in the Otto cycle, it would follow the law, the curve P into V raised to gamma is equal to constant, and the compression would be from the initial state, which is equal to the atmospheric pressure and atmospheric temperature, and the volume will be equal to the total volume as explained in the earlier lecture. So we would be compressing the charge from 1 to 2, that is, this would be the compression from 1 to 2, and it won't be a straight line, it would be a curve. Following the curve, P into V raised to gamma is equal to constant. So this is similar to what has been represented earlier in the Otto cycle also, right? But the next process is different. In the next process, it is a constant pressure heat addition. So the pressure is constant, unlike in the Otto cycle. So this is how we represent the process 2 to 3 on the diesel cycle. Now why it is horizontal? The reason is the pressure is constant. So P2 is equal to P3. Okay, that is why I have represented it like this. The next process is expansion process. Again, it is an isentropic expansion, and now the expansion would end till the total volume is regained. Okay, so this is the expansion from 3 up to 4, following the law P into V raised to gamma is equal to constant. Expansion, so the pressure would decrease, the volume would increase from V3 up to the total volume V1 is equal to V4. So this is from 3 to 4, and then this is obeying the law P into V raised to gamma is equal to constant. It is a curve, and finally it is a constant volume heat rejection. So volume is constant. So volume is constant, so it has to be a vertical line. Volume is constant, so it has to be a vertical line downwards, because heat is rejected, pressure would decrease, the volume remains constant. V1 is equal to V4 is equal to total volume. Here V2 is equal to clearance volume. Okay, so this is how we represent the diesel cycle on the pressure volume diagram. Now representing this on a temperature entropy diagram, we need to consider two lines. One is a constant pressure line and other is a constant volume line. Now you start with state 1, which is the initial state at a temperature equal to the ambient temperature, and there is a compression. So compression means the temperature would increase, and I will try to show it by a horizontal here. It would be a horizontal line here. Okay, why it is horizontal? A vertical line here. Why it is vertical? It's vertical because during the process 1 to 2, the entropy remains constant. So S1 is equal to S2. So it is a vertical line 1 to 2. Right? Why the temperature increases? Because it is a compression. So the temperature increases. T2 is greater than T1 and S2 is equal to S1. So that is why it is a vertically upward line. Then there is a heat addition. So when there is a heat addition, entropy would increase. So S3 has to be greater than S2, but the pressure remains unchanged. So pressure remains unchanged. You move along the constant pressure line towards a higher entropy, which is 3. So this is 3. Entropy increases because heat is added. Temperature increases because heat is added. So temperature T3 is greater than T2. The next process is an expansion process. Expansion, but the entropy remains constant. Expansion, temperature will drop down. So it has to be a vertical line, vertically downwards, such that the entropy at 4 is equal to entropy at 3. So this is isentropic. Entropy at 4 is equal to entropy at 3. And temperature is lower because there is an expansion. And finally, there is a heat rejection in the process 4 to 1. So the entropy at 1 would be less than entropy at 4. Entropy would decrease from S4 to S1. Why would it decrease? Because heat is being rejected. And it is a constant volume process. So we need to move along a constant volume line as shown over here. Entropy decreases from S4 to S1 along the constant volume line, and heat is rejected. So the temperature also reduces from T4 to T1. So this is the representation of the diesel cycle on the temperature entropy diagram. Similarly, we can represent what is known as a dual cycle also, but I'll quickly represent that. Dual cycle is a combination of Otto and diesel cycle in a way, where you have a constant entropy process 1 to 2, then followed by that there is a constant volume heat addition. I am quickly drawing this PV diagram similar to the Otto cycle, but then there is a constant pressure heat addition similar to the diesel cycle, and then there is an isentropic expansion similar to both the cycles, and finally there is a constant volume heat rejection. Okay, then representing it on a temperature entropy diagram, I will have to draw two lines. One is a constant volume line and constant pressure line like this. This is a constant volume line like this. So this is a bit complicated. This is constant volume line. This is constant volume line. This constant pressure line is slightly flatter. Okay, now I am representing it. 1 to 2 has to be vertical. Why it has to be vertical? Because it is isentropic compression 1 to 2. Then there is a constant volume heat addition from 2 to 3. There is a mistake over here. This is 3 to 4 and this is 4 to 5. Okay. So 2 to 3 is constant volume heat addition. So the entropy would increase from 2 to 3. Temperature would increase from 2 to 3. Then there is a constant pressure heat addition. Again, entropy would increase from 3 to 4. Temperature would increase from 3 to 4. And then there is an expansion which is isentropic. So isentropic means it has to be vertically downwards because the entropy is going to remain constant. 4 to 5 is isentropic expansion following the law P into V raised to gamma is equal to constant. And finally there is a heat rejection, which means the entropy is going to decrease along the constant volume line. Okay, and the temperature is also going to decrease. So this way the dual cycle, which is 1 to 2 isentropic compression. This is how it is represented. This is how it is represented. 2 to 3 constant volume heat supplied. This is how it is represented. This is how it is represented. 3 to 4 constant pressure heat supplied. This is how it is to be represented here. Okay. 4 to 5 isentropic expansion. This one, and finally 5 to 1 constant volume heat rejection. Constant volume heat rejection. This is constant volume heat rejection. This is constant volume heat rejection. So this completes the discussion on the dual cycle. So in this lecture, we have discussed how to draw the diesel cycle and dual cycle on a pressure volume and temperature entropy diagram.